Today we're going to be speaking about Oracle forensics, and specifically the dissection of an Oracle attack in the absence of auditing. Often in my line of work, which up until recent days has been more in the attack side of things, what we'll often find during those reviews after a successful penetration is that auditing was not enabled. So if auditing is enabled, then the job of an Oracle forensics examiner is going to be that much easier. But if it's not enabled, how does one then go about gathering evidence after a compromise? Indeed, how do we know if there's been a compromise or not? So why Oracle forensics? Well, since the state of California passed SB 1386 back in 2003, another 34 states have followed suit. And there's legislation currently, I don't know whether it's your House of Congress or the Senate, but they're talking about enacting a federal law. And so the problem, well, not the problem, the idea behind these database security breach laws, or data breach laws even, are that in the event of a customer's personally identifiable information being stolen, they are to tell their customers of the compromise. Now, we obviously saw at the beginning of this year the TJX case where just short of 46 million credit card details were stolen, and that database compromise had been 2 years basically in the offing. So obviously it's the largest breach known so far, and I say known so far because of course we don't know whether there's other databases out there that have been compromised and people just don't know what to look for and they just think everything's hunky-dory. So if we look at the statistics, since these database breach laws have been introduced, in the first 3 months of this year, there are 85 breaches, which, if projected, is going to obviously be 2006, 2005, and so on. Now, in all fairness, these publicized breaches do not necessarily just involve database compromises. They may include a lost or stolen laptop, for example. So it's unfortunate that the source of this data doesn't define whether the breach has been, breaches occurred due to a lost laptop or an actual database compromise. So, given that the law, certainly in 35 states, tells someone that in the event of a compromise, you have to alert your customers to that fact, how do you know whether there's been a successful compromise or not? Well, one would think you could just go buy or download a tool to do an Oracle forensic analysis a forensic analysis of your database server. But as far as I can see, there are 0 tools out there that do this kind of thing. There are tools that can be kludged in a sort of certainly not in a forensically sound way, but there are tools you can do to certainly ascertain whether they've been compromised or not. But by running these tools, you might end up invalidating any evidence. Now, as an example of this, Logminer can be used to read the redo logs on Oracle. But to do that, you've got to alter the system to be able to get access to the redo logs themselves. So in the act of doing that, that's going to change the system in a fairly drastic way, which could potentially cause any evidence to be viewed upon skeptically in a court of law. Now, added to that, Logminer itself will not show, for example, the text of DDL operations, DDL being data definition language, things such as create procedure, drop table, or whatever. So there are shortcomings to Logminer. You could use BBEd, the tool that Oracle used to supply to examine data files, but because BBEd has write capabilities, how would you then go about proving, once you've examined a data file using BBEd, that there was no alteration going on there? So there are tools that you sort of can kludge and fudge your way through an analysis, but suffice it to say that by running these tools, you can potentially damage evidence. So specifically with Oracle, where is the evidence going to be found? Well, pretty much where you're going to expect it to be found. In the log files is a good start. But beyond that, there are the transaction files, what's known as the redo logs in Oracle. And there's the archived redo logs as well, which are sort of, the backup version of the redo logs. The data files themselves provide a wealth of information with regards to, compromises, the metadata and statistics that are recorded in the data files. And obviously, if there's an Oracle application server stuck in front of the Oracle database server, the Apache weblogs themselves will provide an enormous wealth of information. The talk today is specifically going to concentrate on data files, redo logs, and in there we'll be looking for evidence of the creation and the dropping of objects, and so on. Now, that's all well and good if a user starts, or an attacker, not a user. If they start creating objects, these things are fairly easy to find. But if they're just doing a select, for example, your website might be vulnerable to SQL injection, and they do a select to dump credit card information, a union select to dump credit card information of all your users on your website. How would you go about finding, in the absence of auditing, that someone actually performed a select there? And let's say the inject point was via post data, and you're not logging post data on your web server, then unless you've got a sniffer running or some other means of doing this, you're never going to find out if someone's done a select such as that. Well, that's what we'll be looking at the end of the talk, is ways to ascertain whether someone has stolen data through select statements. So first and foremost, though, we're going to look at data files, specifically the metadata in there. So we're going to start off with the Oracle data block. Okay. Database server needs to store data somewhere. That goes in the data files. The data files themselves are split up into a variable chunk size. Now, the default is 8,000 bytes on a Windows box, and each block of data has this kind of format. The grey, I'm colorblind, so I hope I've got the colors right here. The grey at the very top is the header. Below that is a table directory, and that's the light grey. The yellow thing is the row directory. We'll speak more about the row directory in a second. Data itself grows from the bottom of the data block upwards towards the header. And the row directory grows downwards towards the row data itself. In between is free space. Now, what is this row directory? The row directory basically is a bunch of 2-byte entries that point to an offset into the row data. Do we have a laser pointer actually at all? Any chance of getting a laser pointer? Great, thank you. Ooh. Thank you. Ooh. Cheers. Okay. Thanks very much. Okay. So in here are 2 bytes. It's a directory of 2 byte sections, basically, that are an offset into this section here. And the offset starts from the beginning of the row directory. So if we see in there, for example, 2 bytes being 0x1758, then we just add that to there, and we can find the beginning of our row. Each row of data in the row data block has a 3-byte header. The first byte indicates the row state. So, for example, if the row has been deleted, the 5th bit of the first byte of the flags, in other words, it's set. So 0x2c will become 0x3c. So that way, very quickly, we can ascertain whether, if we're looking at a given row, whether it's been deleted or not. The second byte, we can ignore for the purposes of this discussion, but the byte number 3 tells us the number of columns in the given row. After that, the row data itself occurs. Now, the first column, obviously a row of data is split up into columns. The column length of the first column is preceded by the number of bytes as specified by the column length. So here we can see column 1. This is an example row of data. The first number is 04. This is after the row header, by the way. First number is 04. And that indicates there are four bytes of data that fill this column. So C306132F there. And once we get, count 4 bytes in, we then know the next thing we're going to come across is the length of the next column. So it's 04, so we count 4 more in. And then the next one is 02, so we count 2 more in. Then 0D, so we count OX0D bytes in, and so on. Unless we come across an FF. FF simply represents null. It's always 1 byte, and you don't precede it with the length. So you don't go 01 FF. So we trace that all the way through, and obviously by the time we get to the very end, this number here should equal the number of bytes in the row header. The number of columns counted should match up with the number of columns as specified in the row header. So that's when we know when to stop. Okay, so let's say someone comes along and compromises someone's database server, and they start creating objects. A typical attack, for example, in Oracle, would be where there's a PL/SQL package or procedure which is vulnerable to SQL injection, and let's say it's owned by sys and uses definer rights. In other words, when someone executes that procedure or package, it executes with the privileges of the sys user. Now, sys being DBA, being God essentially on that database server, if it's vulnerable to a SQL injection flaw, then an attacker can come along and inject SQL that will execute as the sys user and allow them to gain complete control of that database server. Now, a typical way an attacker might exploit that is if they have the create procedure privilege, for example, Scott or anyone with the connect role, they can come along, create their own nefarious function, stick it, specify a pragma of autonomous transaction, create the function as authID current user. So when it's injected, when this function is injected into the sys-owned procedure, it will gain the privileges of sys temporarily. And in there they specify, for example, execute immediate, grant DBA to public, or do something equally nefarious. So an attacker in the course of compromising a system might go around creating objects. And after they've created these objects, done whatever they want to do, they might go after themselves and clean up to attempt to hide any evidence of their presence. So if we were to spend some time looking for these dropped objects, if indeed they did drop them, if of course they didn't drop them, then they're there for, easy to see. If they did, of course, drop them, then we can go around hunting them. But before we can start hunting them, we need to work out what happens when you go around creating an object. So essentially, the first obvious thing is a row is entered into the obj$ table. The obj$ table is obviously where every object is tracked in Oracle. Again, a wee bit of feedback here. Not only that, but there are 3 indexes on the obj table, IOBJ1, IOBJ2, and IOBJ3. IOBJ2 specifically has, as well as the object ID like the other 2 have, it also has the object's name as well. So, and then depending upon the object type, if you're creating a table, there'll be a row inserted into the tab $ and the col $ tables, obviously for the columns of the table and for the table name and so on. If you're creating a function or a procedure, rows are inserted into the sources or the source table, source $, IDL, UB1, and so on. So when we create a given object, information about that object is stored all across the data file, the system, the system table spaces data file. And when the object is then dropped. Just because it's dropped, it doesn't mean the information's completely wiped clean from the data file, and we can find evidence of this. So what happens is when the object is dropped, simply the flag in the row header of that row of data, the bit is simply flipped. Remember we spoke about that. The fifth bit of the first byte of the row header indicates something about the row of data, and if the fifth bit is set, it will become OX3C from OX2C. So we can then basically open up the system DBF file, and for each block of data that has a row, that is owned by has an object ID of the obj table, for example, we highlight every single one of those data blocks, and then using the row directory, check the offset. That will point to the row header. If it's 2C, it's not deleted. If it's 3C, it is deleted. So we block that out. We also block out the live rows in a different color. So what happens is eventually in the row data section, we have these nice little colored bars essentially with white space in between. Those white spaces will be fragments of deleted data as well. So we can essentially block out live rows, deleted rows, and fragments of previously deleted rows. And of course, we rinse and repeat for every single object of interest. For example, the sources table and so on. Now, remember we spoke about the indexes earlier on. When we drop an object, the index, like the IOBS2 index, still maintains information about the object that's just been deleted. And so not only do we look at tables and so on, but we can look at indexes and so on too. So here's an example. This here is the row directory in there. This here is that's the row directory here. This here is the header stuff of the data block here, and here is the object ID of the table that is filled in this this data block, and in this case it's the sources table. Now, if we follow each of these directory entries and down to the to where it points to in the file from the offset just there, we can see that this one points down there and that one points down there, and they all have 3C. The fifth bit is flipped in that row header. So we can see that all this data here is deleted data. We'll come back to this image in a minute. So after we think we've been compromised, so we open up the system DBF file and start going through each data block that is owned by this object ID here, which is the object ID for the obj dollar table. Now, we see here, after going through everything, that there is a directory entry just there that points to its row data, which is here, but we see that the fifth bit has been flipped and it's 3C rather. So we know we're looking at a bit of a deleted row here. So we then need to crack out the data from that. Looking at the row header, we see it's deleted. That's the log status stuff. We see that the third byte of the header is OX11, which is 17 in decimal. So we know there are going to be 17 columns. This here is the data we'll be looking at, and we'll split it out. So given that we know that there are 17 columns, if we look here, that 04 indicates that the first column has 4 bytes of data, so we count 4 in, 1, 2, 3, 4, and then we get another 4, 1, 2, 3, 4, then is that a 02, so count 2, and then 0D, and so on. So you see how that's happening. We count 4, 1, 2, 3, 4. Then we come across another 4, so this is column 2, 1, 2, 3, 4. Column 3 is 0, 2, so count 2 bytes, then 0D, and so on, all the way down. So eventually, when we do that, we can break down our data into this format, like so. And we count the rows, and there indeed should be 17. Hope there are. There's 17 rows, 17 columns, rather, split out. 17 columns, not 17 rows, my mistake. Now, knowing the way the obj columns are laid out, the first column is obj hash, which is the number, then the data obj number, the owner is next, and then the name of the object, and so on. So, knowing how to dump this data, C1 would indicate a 1-byte number, C2 a 2-byte number, C3 a 3-byte number, and so on. And this is basically the formula for getting it. So you take the number, subtract 1, multiply it by 10,000, take the next number, subtract 1, multiply it by 100, and then add, and so on. So you eventually get the object ID number is 51846, and the data obj number is 51846 as well. The owner is 55. We don't necessarily know who that is yet because we would need to compare the user table with, that correlates to user 55. But we can see that there is, the name of the object is myTempTable. And this is the date upon which the object was created. So this is the M time, the C time, and the S time. If we take that object ID and just do a simple binary grep through the rest of the system DBF file, we find this object ID is revealed elsewhere. For example, in the monmods table, the imonmods index, the recycle bin, and this cluster down there. Now, once we've gone through all that, we start looking for evidence in the sources table and so on. Now, what happens is, when we come across that, this is the image we looked at earlier, we find that there's a deleted row, a bunch of deleted rows by following, as we spoke about earlier, each entry in the row directory, you follow it down, from its offset. So we come across all this stuff. So this is the address offset in the system DBF file, plus that entry in the row directory. We go to that address and we find the deleted row. Now, when we look at these deleted rows, we find that they all have the same object ID, 51850. So we know that these deleted rows are all part of the same object. If we look at the text, you can see the text obviously in the ASCII text here. If we crack that out easier so it's easier to see, there is a function called extract syspassword return varchar, auth ID current user, pragma autonomous transaction, and if we look here, it's doing an insert into scott.myTempTable. That should obviously, we should be thinking, wait, myTempTable, that was one of those objects we saw dropped earlier, and it's selecting the syspassword hash and dumping it into that table. So clearly we're beginning to build a picture up here as to what's going on. This looks like Scott's come along, created an object, a function object, that he's got all all the hallmarks of an exploit, i.e. auth ID current user, pragma autonomous transaction, and it's doing an insert. Pragma autonomous transaction is, hey, it's okay to run this, go ahead and do this. It's not going to change the state of the database over whatsoever. But it is, clearly, because it's doing an insert into myTempTable. So we can see that this is probably indicative of an exploit being run. Now, given that we know the object ID of the myTempTable, 51846 and so on, given that we know where that is, when we go through the other data files, we look at the users table space and we find evidence of this table in the user's table space. And we can see down here, sorry, that's the object ID there. This is the start of the data block. Here is the data that's been inserted. So that there is the password hash for the sys user. So we can see that someone has definitely exploited this, exploited our flaw to inject their nefarious function, which inserts the sys password into a table owned by them. Okay. So that's how one would examine the data files themselves. Now, given that a data file might contain 36,000 rows, or whatever, of information we would need to search, it's going to take us a long time to do that manually. So eventually, I'm going to be releasing a tool called FEDS, which stands for the Forensic Examiner's Database Scalpel, that will automate all this process. Unfortunately, I didn't get the time to get the tool written up in terms of releasing it today. But watch this space. So the next aspect of looking at a compromised Oracle server to ascertain whether a compromise is taking place, or if they have, what's the extent of the penetration, we can start looking at the Oracle redo logs. The redo logs exist so that in the event of a database failure, in other words, the system cuts out, for example, a power outage or whatever, then actions that were done before they were written to the data files can be redone. So the redo log contains entries, of course, and a redo entry contains all the given changes for a system commit number. The system commit number is, last time we committed to the system, the number was this, and so on. So all those changes are written in a specific redo entry. So there could only be one change, or there could be multiple changes. The redo entry has a header with one or more change vectors. So what do I mean by a change vector? Well, a change vector is an action that was taken before the database failed. So the operation code for an insert on a single row change vector would be 11.2, delete 11.3, and so on. Now, one of the interesting ones is DDL 24.1 down the bottom. For the vast majority of these lot, well, in fact, for all of these lot, with the exception of DDL, you never see the text of the SQL that was executed. For example, you never see insert into sysorf dollar, whatever kind of thing. You never see that. But what you can do is break it down by looking at the opcode to see there was an insert, checking what object ID the insert was performed upon, looking at what rows were inserted, and so on, which we'll obviously look at in a second. But 24.1 DDL indicates a data definition language operation, and the text of that is now stored in the redo log itself. So, for example, if someone goes and creates a user account for themselves, that text will be there. If someone creates a table or a function, that text will be there. Certain alter statements will be there as well, and obviously drop and so on. Now, this is a section of the redo log, and you can see up here this is an insert example basically here. Right there is the opcode for insert. So we know that we're looking at an insert here. On the left here is the timestamp. Now, obviously, when you're doing a forensic analysis, time is important. Now, the question is the time related to when the insert actually took place or when the record was written to the redo log? It's actually when the record was written to the redo log. So if the system hasn't flushed changes to the system or written it out to the redo log, there might be a considerable lag between an actual insert taking place by an attacker and it being written to the redo log. Now, as long as you can account for that, that time difference, then it's fine. Now, here we can see the user ID down the bottom there of the person who did the insert, which then we can refer back to the user table and work out, what their name was. And we can see the data that was inserted. So we see C102, which means the first row is value 1, then C105, which means the next row is 4, and then C2, so that's 800 and something or other. Now, when we look at the object ID, which is there, we, having dumped the data dictionary, know that the object ID the name of the object that correlates to that object ID is sysauth$. So one has to question here, who the hell is inserting into sysauth? Sysauth$ keeps track of role privileges and so on. So if you're a DBA, there'll be a row entry in there for you. Now, given that we know what sysauth, the columns are, what's happened here is someone has done a direct insert into the sysauth table to give the public user/role, whatever you want to call it, DBA privileges. So that is not normally what would happen. If you're granting privileges, there would be a DDL entry. There should never ever be a direct insert into this table. If we actually dump this number here, what we actually find is that it's one more than the previous. It's like a unique constraint. I can't remember off the top of my head what it is, but suffice it to say that it's one more. So probably what the attacker's done, and without direct evidence of this, is a purely supposition, of course, is that they've just selected like max and added 1 to it. So this, by dumping this insert from the redo log, we can see that something nefarious is going on. So we already mentioned the timestamp is when the redo entry was written. It's not when the action was taken. How is time recorded in the redo log? Well, it's basically the number of seconds from midnight, 1st of January, 1988. Don't know what's special about that date, but what's interesting is if you set your computer clock to a date before that, Oracle 10G will stop working. So here's a nice DDL example. We can see, and again, this should immediately raise our hackles on our neck, because we see that the user Scott here has executed create user wiggy 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 identified by values, whatever the password is, kind of thing. Now, this here is the schema in which the action took place. This there is the executing user. Now, oh sorry, that 1801 there, 18 in is the hex for 24. So that's the opcode for the change vector for a DDL operation. But the important point here is Scott is the executing user, but the current schema is sys. So that probably indicates that he has created this user via a SQL injection flaw, PL SQL injection flaw. Again, I say probably because without actually seeing the actual injection flaw going across the wire or in a log somewhere, we just have to make an assumption. But suffice it to say, we know that Scott was the guy who did this. Now, how are we doing for time? What about evidence of selects? There are no objects created during a select. There are no transactions that occur during a select. And for those Oracle people out there who go, yeah, what about a select for update? Well, yeah, okay, accept that one. But when someone's stealing data, they're not going to be doing a select for update. It's just going to be like, for example, let's say they're coming in via a web application and they inject a UTL HTTP.request, come back out of your network, post to me via a web server, using UTL HTTP request, the data I want to select. Well, there is no object created in that time, or there's no transaction or whatever. Simply there's stuff posted out. Or if it's not a blind SQL injection scenario, it's just dump the data back via a union select into the web browser. So, having looked around and poked the system, there are actually evidence. There are places where evidence of just plain old selects can be found. These include the automatic workload repository, the cost-based optimizer, and of course the fixed view VSQL. So, what is the cost-based optimizer? Whenever anybody executes a query in Oracle, that obviously has to be compiled into a query tree, an execution plan, in other words. Now, the most efficient way of doing that is selected by the CBO, the cost-based optimizer, and it does so with the intention of reducing pressure on system resources. Now, information about the CBO and the decisions it makes and everything like that are monitored and tracked by the system monitor background process. Now, one of the tables where information is stored about this is in the call usage table. Now, in terms of actually getting something useful out of it, it's not like a smoking gun kind of thing, but it's just, it does provide useful evidence. But again, we don't get to see the complete SQL text here. We can infer. This table can be used to infer information about what selects have taken place. So if we dump, if we describe the call usage table, we can see that the first column is hash, which is the object ID of the table upon which a select has been issued. The int col is the column number that was selected and so on. And these predicates here are essentially a while, a where clause. So for example, this like preds here would indicate that someone has done a query like select password from DBA users where username like sys%sys, syn% quote kind of thing. Now, that would cause the CBO to add an entry for the DBA user's object ID and the column for the password, and the like predicate would get account number 1 and so on. And obviously the timestamp upon which this all took place at. Now, given that we may have been compromised, we can look at this call usage table, but with no frame of reference, we don't know whether there's anything untoward in there. Well, we can compare copies of the current call usage table to copies in our backups. Another way to do this is look for odd entries. For example, if we know we have no application in our company-wide web applications never request data from table X, but wait a minute, there's an odd entry for table X in this call usage table, then that might indicate foul play. So for example, let's say there's a, let me think of a suitable example. For example, DBA procedures. No one ever queries DBA procedures because we're in a production environment now, everything's ticking over, it's been ticking over for the past 2 years, and no one should ever select from that table because we don't need to modify the procedures anymore. But suddenly we find an entry in our call usage table where someone's been analyzing procedures that are in our web application. Let's say we've got a web application that's using the Oracle PL SQL Gateway, and they've broken in, they're trying to ascertain information about our PL SQL application on the back end. They might query DBA procedures, or they might query, for example, argument $. So if we find entries for this in there, and we know none of our applications request from there, or none of our users are supposed to request from there, or there's no database job or anything like that doing it, then it should be cause for concern and a reason for investigation. So what we would do, obviously, is marry those object IDs in the column number 1, with the object name in obj$. And if something stands out, by the way, whenever you're doing a forensic analysis of a compromised database server, you should always do it in the presence of the DBA, because the DBA will know instantly when something's wrong with his system or something is untoward. For example, if you, as a database forensic examiner, looked at the users table, and you would look through the users and see, Jim, Jane, John, whatever kind of thing, you're not going to know whether they're valid users or not, but the DBA is going to instantly recognize that Jane, there's no Jane who works for us. So you should always do it in the presence. If you're not, of course, the DBA doing it yourself, you should do an evaluation, forensic examination rather, in the presence of the DBA, because they should instantly spot if they're worth their weight anyway. So here's an example. By the way, the reason we do the auto session and set the time format to this is because otherwise we would just get 31st of July 07, which isn't really that. when we require decent timestamps, we need it down at least to the second. So we can see when all these took place. There's an object 21. Don't know what was that a question? Sorry. There's a table with an object div 21 that has been queried at some point, and we can see there's an equality pred down here. Like preds, no one actually used a query on that, but you get to see what's going on. So anything in here that shouldn't be in there should be cause for concern. Now, the automatic workload repository is a way of for the system to keep track of how well it's doing in terms of performance, basically. So every second, the system will take a snapshot of executing SQL, and all this is written to a data file somewhere. Now, SQL that takes a long time to execute is obviously going to get, more noticed and end up in these tables more than others. So, for example, as I already said, if someone's injecting UTL HTTP request to exfiltrate data somehow, because there's a network round trip involved in that, that's going to take a long time. So we'll find entries in these tables, essentially, that record in its entirety the select statement. So one way we could do this in the automatic workload repository is combine the stats with the text and dump basically all the SQL text there. There should be another one. Here we can get the, no, that's not it. Sorry, I was missing a slide there. Which query is it? This one here you can use obviously to dump information about a given user ID that's performed a certain query. Let me put it in Notepad so you can see it clearer. So you can see here we're specifying the user ID. We're interested. Let's say the user account with that user ID we think it's been compromised. We can basically go through these things looking for actions that they may or may not have taken. So let's do this. So you can see we're dumping out select statements here. So, funny enough, the statement we've just run is now in the, because it took a long time, it's now in there, So we can see an update has taken place, and some trigger thing has taken place. Now, we can also do Actually, we'll come back to that later. Suffice it to say that the automatic workload repository is an extremely useful source of information. The $SQL view is what's known as a fixed view. These fixed views are basically in-memory resident. So when the database is shut down, it's gone. So if your company policy is such that in the event of a compromise, unplug from the network, shut the system down, you might be losing potentially valuable evidence. One of the interesting problems, actually, with the whole live response thing is in Britain we have what's known as ACPO. It's the Association of Chief Police Officers. And they wrote some guidelines on how to do a forensic analysis, and they basically say you're supposed to go and photograph the screen, and if the screen's turned on, and barely touch the mouse and shut the system down, pull the cables out and everything like that. Well, that it's clearly been written with the guidelines for performing a forensic analysis of a potential criminal. You boot their door down, you go and grab their PC and what you should do and everything like that in terms of maintaining evidence. I don't think it was ever intended to be guidelines for the compromise of an Oracle database server in the back end of nowhere. So the legal question is, if you're performing a live response on a compromised database server, is that going to invalidate any evidence? Is that going to make it impossible to pursue criminal charges? I don't know the answer to that. Does anybody know the answer?
As long as you can reproduce what you do, and you don't can't leave the data.
You don't think so? But surely, because it's a live response, you are in some way modifying it,
Right.
Modifying the system.
You are modifying the system, but if you can document how you modify it.
Yeah. Okay, that's what I thought, but without having, are you a lawyer or I'm just wondering if that's your opinion or whether it's
Well, it's the same thing if I'm doing a hard disk analysis now.
right.
If I could document what I did, then
But in terms of a live response, you wouldn't be doing a live response on a hard disk, surely. Yeah, sure. Okay. It's just I've been mailing out to lawyers and ACPO, and they don't want to seem to talk to me. Don't know why. But yeah, it would be really good to get an actual legal answer to this question. I'm sorry? Sorry? Dump the physical memory. Sure. So I completely concur. I published a paper a couple of months ago called Live Response that deals with, what to do with a database server. And, one of the things is obviously dumping physical memory there. What's interesting in that, of course, is though that one of Joanna's recent talks was defeating hardware-based RAM acquisition tools and everything like that. And I don't know if you ever saw that talk. I'm not sure if the slides are available, but it looks quite interesting. Anyway, that's an aside. No, but if you've got a compromised server and someone does hardware-based RAM acquisition, how do you know that someone hasn't loaded up that kind of thing into the database server? So I'm just saying it's like it's always an arms race, isn't it? Someone comes up with a new idea and then someone defeats it and so on, kind of thing. So okay. So the SQL text is a fixed view in memory, and of course, we can get this from a memory dump and so on. Or if we're doing a live response, then we, in a very controlled fashion, and of course documenting the way we do this, connect with for example, we could connect with SQL+, having reviewed glogin.sql and those SQL things that run in the background, of course. and we can simply dump the data from memory that way. So, just as an example of this. So we can go, and this here is dumping the name of the user that executed the SQL and the parsing ID and the parsing schema ID. So again, if these things don't match, if for example there's an entry in there with the parsing user as Scott and the schema as sys, that might be indicative of the SQL injection attack. It might also be, of course, indicative of someone going alter session set current schema, and changing the schema. But we spoke about live response and taking actions that actually modify itself. You can see now that the previous query we run to get access from the automatic workload repository is now listed in here. So actions we take are now overwriting stuff in the $SQL. It's like a circular buffer, basically. As new stuff comes in, the older stuff gets bumped down. So if you're doing a live response, the very first queries you should run are, select from this view, select from the automatic work repository, and so on. So you're not influencing too much. You're not bumping up too much stuff. And then you can go on and do, dump the other information with regards to, users, object IDs, object names, and so on. So this actually brings us to the end of the presentation. Obviously, in review, all we've done essentially here is looked at the data files, specifically the metadata themselves, ways of getting access, information from the redo logs, and looking at things like the system monitor tables to access information about selects, and also the automatic workload repository. So there are other places where evidence can be found, of course, the TNS log files, trace files, and so on. So that we'll save for next year, I suppose. Are there any questions regarding this stuff at all? Tim, you're always good for a question.
I have a valid one, actually.
All right, cool.
The SQL select statement that's resident in memory.
Sure.
Do you have any insight into how deep, how far back the history goes?
Well, it depends on how many queries are being run. There's usually about 1,000 queries in the buffer. Now, obviously, a anti-forensic attack on this would be one of the last things an attacker does is fires off 1,000 queries. That's obviously going to bump out, his real attack. So it might be select, 1 from Joule, select 2 from Joule, select 3 from Joule, or whatever. So each one's different and going to get a new entry in the in the $$ SQL fixed view. So in terms of an anti-forensic attack, you can wipe your stuff. In terms of an anti-forensic attack actually against the redo log, if you've got DBA privileges, you can just alter the system and completely delete the redo logs and everything like that. So
you need to have access to that pretty quickly after an attack.
Sure, but in terms of the anti-forensics attacks, there are definitely attacks that are possible that make it harder, and then you've got to just, work a little harder to get the evidence back. Because obviously, when you wipe a file, supposedly, you can still get that information back off again and everything like that. Or if you delete it off the file system, then it's still going to be there. Sure.
Your presentation focused on the deletion of the road.
Yep.
Would these techniques still apply just on the modification of rows as well?
Sure. So if you update a row, what typically happens is, depending upon which elements, which columns of the row you're updating, if it's numeric, it usually stays in the same row. But if it's like string-based, then what will happen is you'll get a new row being added to the top and the old one sort of invalidated. So yes, if it's being updated, then you can still get evidence out. It's done in a slightly different fashion. And of course, if they're not dropping the objects, they're just creating them, then that's when the presence of the DBA comes in useful, because he can say, wait a minute, what's this my temp table, or what's this get DBA function, you know? So, sure? I'm sorry? Yeah. Very well could do, I don't know. But that's an excellent place to start looking. And also the undo table space, of course, is another place where, you know, that's good for evidence too. Sure?
Even table spaces where the rows are either deleted or updated or otherwise modified, it seems to me like that would be at least partially susceptible to coalesced table space. Is there anything that is completely inviolate, at least at the time of the presentation?
I don't know. So here's the thing. If you Google Oracle Forensics, there is so little information out there, and I mean, Paul Wright, one of my colleagues, posted a paper a couple of years ago, but it's completely under research, and all these things like the the temp table space and what you're saying, don't know. But these are things that need to be researched and added to the corpus of knowledge with regards to Oracle Forensics. You know, so sorry, this gentleman next. With great difficulty. I mean, but in all seriousness, without this stuff, it's even harder, you know? But at least this way we can try and narrow it down a bit better and stuff. Sure, JD? Most of my research currently is on 10G Release 2. Although I've looked at, you know, does this apply also to Oracle 9 and so on, or Oracle 8? For example, with the redo logs, the DDL text is not there in Oracle 8. And I think it was introduced in Oracle 9i Release 1 or 9i Release 2. So it depends on the version of Oracle whether this stuff is applicable or not, or some of this stuff is applicable. But in terms of the way data is managed in the data files, I think that's pretty much, you know, standard throughout. Sure, over there?
Questions first. Is there any kind of like security flag you can set on a table so that the data is actually secure from the table?
Not that I'm aware of, but there very may well be. The thing, of course, is if you compromise the database, then you can simply use Java or UTL file to just wipe out blocks within the actual data files themselves, because Oracle will open the data file in a sharing mode that allows other people to write to it still. And because if you're using the Oracle database server, for example, through a Java procedure or through UTL file to write to it, well, you're doing that with the privileges of the Oracle user, so you have the privileges as well to write to the data files. Now, what's more, you can, provided you know the way the checksum is generated, which is each data block has a checksum that basically takes 16 bytes of blocks and XORs them with each other, and that becomes the checksum. Now, in one of the papers I published on the dissecting the redo logs, I actually talk about the checksum and write some code to show you how the checksum is done. Now, in terms of an anti-forensics attack, of course, it's possible to use UTL file or whatever to overwrite stuff in there and in the data file, jig the checksum to make it fine, and Bob's your uncle, the database keeps ticking over and your evidence has almost been obliterated. But if you think about when you do that, when you use UTL file, that might be in the automatic workload repository, and then when you try and hide that, you're going to bump down the evidence elsewhere, kind of thing, Sure. No, the workload repository should keep on building up and building up. But the $SQL text is like a circular buffer in the SGA, and that gets overwritten, as new stuff comes in. Sorry? The redo log, if it's not in archive mode, eventually that, again, it's quite, it's circular. Old entries are overwritten kind of thing. But if it's in archive mode, then for each cycle of the redo logs, an archive, a backup copy is essentially written to the disk. So, you should have copies of these. Well, it depends on what you choose to back up. If you choose not to back up your system data, then obviously we can't go to a backup to examine. If you do have backups of that, though, then that's great because we can actually use this to compare two states of the database with each other and say, well, wait a minute, these three objects suddenly appear and they look benign, but you probe deeper and then they turn out to be like Trojans or whatever kind of thing. Any other questions? Sure. In a storage area network? No. No. Again, as I said, I've only been researching this for, about 6 months now, and much more research needs to be done. We need to, as a group, spend some time on this, basically, because, as we've seen, in the introductory slide, database breaches are actually occurring all the time, and we need to know if they're occurring, how they're occurring, and working backwards from there to prevent things like this from happening again. But no, I have got no experience with SANs at all. Sorry.
You want to have a full database backup. That's the best in case.
Yeah.
So you want to, if you're going to not take the database down, you keep tables up and read only, and then start checksumming DBF files. And
Yeah.
log files and try to.
Well.
So in that case, the NAS server has a snapshot equivalent.
But if you check some of the DBF files, they can't be written to, because the checksum's immediate. And plus the fact, as soon as an SCN is written to it, because, the system writes to the database file all the time,
Yeah, we're not using the database, we're using the feature of the NAS server. I mean, that has a snapshot of all your control files on the NAS server. You can take that and you can have a consistency with that. At the previous point in time, with what you have now that you've altered,
Sure.
doing your analysis that
Yeah.
you just did, to, like your question to me earlier, now you can show that you haven't done anything bad with what's your analysis because we have something that's at
Yeah.
even a lower level than the database.
Yeah. Cool. Any other questions? No? Oh, yeah, sure.
We're looking at, they have these new database firewalls that are out now, like RDM.
Yeah.
Do you have any experience and comments on whether
Yeah, it's, do I have any opinion on database firewalls such as Imperva's product and Guardium's and that, pretty much? They're a good source of additional information, in terms of audit trails and everything like that. I mean, if I'm not going to advise you to get one, I'm not going to advise you not to get one. I personally think things like this increase attack surface themselves, and will often become a focus for the attacker and might end up owning your network anyway. Now, I'm not saying anything about Imperva's product or Guardium's product or anybody's product. It's just that we've seen these kind of things in the past where, for example, Snort's been vulnerable to an overflow and they get owned through their alarm systems, or the witty worm that exploited ISS's Black Ice intrusion prevention product, in it. So all you're doing with these kind of devices is actually adding, extra components to the network which provide extra attack surface to the attacker. Are we good then? No more questions? Great. Well, thanks everybody for coming and hope it was useful.